Hi everybody, I am Bonaventura, a doctoral student at the University of Salerno in Italy, working on the dynamics of structures and earthquake engineering. I'm also involved in the DualSPHysics project, working on the reliability of marine structures. Today I will present this work about the numerical modeling of point absorber wave energy converters with power takeoff unit. This work was done in collaboration with Universidad de Vigo and the Universidad Politécnica de Catalunya in Spain. We started this work because we wanted to provide a new numerical tool to support the design phases of wave energy converters. This presentation highlights the robustness of this framework, and because we wanted to extend our model to appeal a wider audience. During this presentation, I will show how to deal with the numerical modeling of wave energy converters through system identification, efficiency, and survivability analysis. First, the main features of wave energy converters will be introduced to give you a better understanding of the complexity of this problem. Then I will use a case study approach to present a comprehensive picture of the tasks that can be performed by using the DualSPHysics framework. Wave energy converters, WECs, are machines that can turn the wave energy into electricity. This chart shows the distribution of research efforts. And as we can see, the point absorber technology is winning this race. The process of energy conversion takes place in several parts of the device. Here, a buoy, which is the part that faces the waves, and the motion of which is transmitted to a PTO system, a power takeoff system, which is the part where the motion is converted into electricity. The numerical design of WECs can be performed considering different operating regions according to the limit states that we are considering. So, for example, we can have power production mode or survival mode. Penalba et al. Charted the fidelity of the available numerical models against the computational cost. Here I introduce two mainstream codes. The first one is WAMIT, which is a potential flow-based code, and here we can see the SPH-based code DualSPHysics. This equation describes the motion of a buoy and identifies the involved physics. So here, apart from gravity, we can see the fluid contribution to the motion of the buoy. And here in this bar chart, we can see that the main contribution comes from pressure. And considering this is done considering a heaving point absorber under regular waves. The last terms of this equation account for our intention to convert the motion of the buoy into electricity. So here we can apply a PTO system, mooring lines, or external control systems. For the simulations performed in this work, we use the DualSPHysics framework where the project chrono library is coupled. Moving on to the first case study, we consider a cylindrical buoy to keep this demonstration simple. And so here you can see the mechanical scheme of this test setup. And we used this device to constrain the motion of the buoy to have only 1 degree of freedom, heave. And here the way we can define a PTO system with a spring in parallel with a dashpot. This buoy was tested firstly under regular waves, considering a piston type wave maker, and the geometry of the flume reproduces the exactly setup that was used for the experimental facility. In the next slide, we will see a validation of this device, which is performed considering 3 values of the damping coefficient. And here you can see the validation, which is performed in terms of heave motion of the buoy. And the simulations give a good agreement for all the 3 cases. With the validated model, we performed an efficiency analysis. In this slide, I reported the main quantities that we need to perform such analysis. So, for example, here you can see the wave power of the wavefront and the power absorbed by a PTO system. This way we can define the capture width ratio and then the efficiency. We used a set of regular waves to identify a spectrum and also to give the results in terms of spectra. So here you can see we are using second order and third order regular waves. Here the results are charted, and on the left the power absorbed by our device, and here on the right the efficiency chart. So these two charts could be used to identify and to get useful information about the dynamic properties of this device. Finally, we performed a survivability analysis considering a focused wave model of the extreme condition that we take into account. Here, the setup of the numerical tank we used, and we considered 3 different floating lines for the device. On the left, the SPH simulations are reported, and on the right, the horizontal and the vertical forces are charted. Here we can immediately identify, for example, the worst case scenario, which is the one where the floater is at free surface. Moving to the last case study, the waveboard studied by the Sandia laboratory is taken into account. Here the lateral shape of the floater, which is a bit more complex than the previous, but in addition we have a complex system of actuators here that are used to mimic the behavior of PTO systems and external control systems. First, we perform a radiation test, which is useful to define the intrinsic impedance of the device. We could use this approach, which is defined by fullness, and to get this function, we should define these 4 parameters. We used another approach, which is the one that you perform. It is performed by considering a radiation test. So mainly we define an external perturbation, which is a force, which is applied here, a vertical force, and we measure the effects of this force, which are velocities. And so building this signal, and by post-processing this signal, we can define these force charts using different operators. Here we compare the SPH results, the results of a WAMIT simulation with experimental results. These 3 charts show a good agreement, and also the resonance point is clearly identifiable. The real part of this signal gives also other information, and we can see that for high frequencies, the SPH model gives a good agreement, whereas it loses some accuracy for low frequencies. A static test is when a device is perturbed by regular waves. So in this case, this is the numerical tank for this static test, and we are using regular waves. Here the validation, which is performed in terms of vertical forces, and as we can see, there is a good agreement between the experimental and the numerical setup. Finally, a dynamic test is performed when waves and an external control system are applied to the wake motion. This way we can define an open loop system, or we can have an internal perturbation, in this case, which is given by the inner system, the inner PTO system. This way we define closed loop systems. Here the setup for this last validation, and you can see how this is the way we define the PTO system, the control loop system, defined as a spring and a dashpot working in parallel. This is the last validation, and as you can see, it's performed in terms of forces and velocities. And also this simulation shows a good agreement. Concluding, DualSPHysics can simulate point absorbers, and this was demonstrating during my presentation. All the external systems that should be introduced to control the movement of a buoy to turn it into a wave energy converters can be easily handled thanks to the coupling with the Project Chrono library. So we can conclude that point absorbers wave energy converter can be studied with the DualSPHysics framework. And here I would like to highlight the robustness of this framework, which can be given by considering that for each test that I shown during my presentation, we didn't change it so much to do different analysis on the same device. So this is something that can account for the robustness of our framework. Here an example of a future work that we are already performing. And you can see a floater, which is attached, a moored floater, which is attached to a complex P2 system. So thank you for your attention. Are there any questions? Here my contact information. Please feel free to contact me.